I'd encourage you to get the notebook. As I usually do in my talks, there will be things in the notebook that I don't cover here. They will be labeled in that notebook as bonus sections. I will not open the bonus sections during this talk. The bonus sections are for you when you get the notebook back into the quiet of your own workspace and to see some additional information, hopefully useful, sometimes humorous. And I'm going to be talking about principles of dynamic interfaces. This is not a talk I've given in the past, although it covers some of the same information. Dynamic hasn't changed a whole lot, but I think we've learned a lot about how to use it. So people in the back row, tell me when to stop up magnifying here. Is that enough? That's okay? Okay. So I'm going to be talking a little bit about... So the talk is going to be highlighting a few sort of high-level principles of how to handle approaching interface programming in Mathematica, how to approach handling dynamics. And sprinkled throughout, I'll be offering some essential concepts and some key techniques for using dynamics. Okay, so start off, high-level principles. These actually were uncovered by Mr. John Foltz a few years back, and try as I might, I couldn't improve on them for this year. So these are the same principles that John illustrated some years back. Principle of programmatic generation, principle of minimal dynamics, principle of maximum encapsulation, principle of evaluation blocking. If you see anybody taking pictures of the screen, please let them know that the notebook is going to be on Pathable, is on Pathable. Hit them with your elbow or whatever you need to do to get them to stop taking pictures. So, programmatic generation. This shouldn't come as a surprise to anybody. You're at a Wolfram language conference, and best way to generate interfaces in Wolfram language is to use the Wolfram language, not to sort of edit the interface files directly, but to construct a program that generates the interface. So what does that mean? What kinds of features do we have for generating interfaces, for putting these things together? Well, there are a set of dynamic primitives. These are the things that underlie the controls themselves. The dynamic and dynamic module allow you to have this nice bidirectional communication between your controls and expressions, or between expressions and other expressions. We have a rich control language, including button, checkbox, radio button. I didn't list them all here. We have nice locator pane, which is our sort of multi-thumb direct access controls. We also have a low-level event handling system, and all of these are listed on these help pages. In addition to the controls and dynamics, we have a rich styling language, a rich layout language, panel, grid, styling. Jason showed some styling. And I'm not going to be talking much about the styling. This talk is mostly about the dynamic stuff, but I wanted to make sure to give at least a nod of the cap to these guys. And for wrapping up the interfaces, of course, you have deploy, create palette, create dialog, these kinds of things. And provided with Mathematica, we take two different approaches to giving you interfaces. There are interfaces built in the Wolfram language that are built once and then burned into the product that we ship you. So the about box is a notebook that someone has written some code to generate. That notebook is saved, pushed into the layout, shipped off to you. Preferences dialog is a notebook. The help viewer toolbar is a cell resource. All of the things in this list and more are resources that are sort of built once and then deployed as finalized things. And then there's the set of interfaces that, they're not generated beforehand. They're generated at the instant that you press Shift-Enter. So if you have a manipulate expression, that manipulate didn't exist before you evaluated it. There's a body of code that ships with Mathematica that gets run when you request to manipulate. Likewise for Wolfram Alpha output in Mathematica. System information and several other things are all code-based. Okay, so I'm going to cover a little bit about what the dynamic primitives are. And the majority of this talk is going to be about certain features of the dynamic primitives. But I wanted to give sort of a baseline understanding of what these guys are. So dynamic is a wrapper that you can put around an expression, and the output of that, the typeset output of that, should look like the value of that expression right now. So dynamic of x, the output of that should look like the value of x right now. If x were to change because of some other evaluation, the output should also update to what x looks like right now if you had x changing more quickly. That dynamic should always be what the value of x is right now. Right, so these are display dynamics. When a display dynamic is handled, how does Mathematica know that when x changes, it needs to change that rectangle on the screen? Well, when it's first evaluated, the evaluation goes through the kernel in such a way that the kernel tracks all the symbols on which that rectangle depends. In this case, it's very simple. It only depends on one symbol. So the dependency graph is built. It's a simple graph, and we see just a single symbol in it. But you could have more complicated dependency graphs. So for instance, here is a rather unimaginative stack of functions. F depends on G and A. G depends on H and B. H depends on nothing. And we have dynamic of f of 3. So this has, this output depends on f, depends on g, depends on a. If you change the value of a, the output changes. If you change the definition of g, the output changes. So any piece of the dependency graph is going to trigger updates to this piece of dynamic output. And it's not going to trigger updates to other dynamic outputs that don't depend on those symbols, right? So each dynamic output is handled separately. Again, the bonus sections I'm not going to be opening at this talk. Please get the notebook, open them yourselves, enjoy. Okay, so dynamic wants to show you what the value would be right now. Of course, right now really means it might be okay for an expression that only updates once, twice, 3 times. Here we have an example of an expression that's updating as fast as it can. In fact, it's the dynamic that's pushing the updates. So dynamic of pre-increment of c, evaluates pre-increment of c. What does that depend on? Well, it depends on the value of c. So the value of c changes during the evaluation of pre-increment of c. So there must be another dynamic update. During that next dynamic update, the value of c changes again. And so we have a dynamic that runs on here. Sometimes this is what you want. Sometimes self-running dynamics are a very useful way to drive animations, to run models, and whatnot. Sometimes it's not. And there are primitives that one can use to restrict the scope of the dependency graph. So track symbols is an option that lets you say, I don't care about this symbol. Don't let changes to this symbol trigger dynamic updates for this dynamic. Update interval is another option that says, if there hasn't been a dynamic update in this number of seconds, trigger one. So here we've now throttled back this pre-increment of c loop so that it doesn't update by virtue of c changing. It updates by virtue of time passing, right? Okay. If I had not set an update interval, it would update once and then be done. Yes, which also sometimes is useful. Thank you, Itai. So on the flip side of that, sometimes updates are too frequent, but sometimes they're too rare, and you can use the same kinds of handles for getting track of those. One thing I'll point out is track symbols is not an additive option. Track symbols does not let you declare a dependence that wasn't there to begin with. So so here we have dynamic of date string. Date string doesn't depend on the value of c. I'm trying to say, well, I want it to depend on c. That's not how track symbols works. If we change the value of c, this dynamic is not going to update. Track symbols is not additive. It doesn't say, update based on values, based on updates to this symbol no matter what. It's this symbol if it's in the dependency tree. And you can force it to be in the dependency tree if you really wanted to, I suppose. That's occasionally useful, and now we see updates to the date. But just to sort of set clear what track symbols is, it's subtractive, not additive. Yeah. Because that's the useful thing. I mean, why would you want a dynamic to depend on some spooky action at a distance symbol? Yeah. Well, and you can do that with this technique. Yes?
Quite often wanted sort of the inverse of this, which is that I do want to pay attention to changing symbols, but not to update more frequently than some particular, like an upper bound rather than lower bound.
Right. So you want yes, you want a feature we don't have. That's correct. Right, and we've already talked about update interval. Okay, so in addition to wanting to be current, dynamic wants to be seen. Nothing is guaranteed to happen when dynamics are off screen, when dynamics are hidden in some way. If they're not shown in a piece of typeset output, nothing is going to happen. If we evaluate dynamic of setting some variable, did that variable get a value? Well, not yet. So here we have a somewhat more interesting example. We have a notebook that has a dynamic and a closed section. So we have an expression cell and a closed section. Has var gotten a dynamic? Has it gotten a value yet? No. When we open this cell group, now the expression goes through. Now it becomes visible on screen and the dynamic updates. So dynamic really wants to be seen. But it doesn't want to be seen by you. It updates when it needs to be seen by the front end. And the reason that distinction is interesting is because sometimes the front end needs to render these expressions before you see them, or even if you never see them. A good example of that are a collection of objects that basically their purpose is to show a set of expressions, but only one at a time. We have tab view, pane selector, these kinds of things. It shows one expression at a time. But with the default styling for tab view, the front end wants to know the size of all of the tab panes in order to size the overall tab view, right? So it needs to actually render every one of the tabs. That's why this tab view is so big, because the default image size for tab view is all. So it looked through here and found the widest pane and the tallest pane and sized accordingly. This is fine and it's useful, but it's occasionally quite thorny. And let me get the messages window up here. I want to show you something. Okay. So why is this thorny? Why am I even mentioning this in a talk about dynamic? Well, so here we have a tab view. Each tab has a dynamic around its contents. This is very common sort of idiom for building interfaces. You have one tab does one set of things and it needs a dynamic display. Another tab has another thing. But you want those dynamics to sort of wait until you switch to that tab to update. By default, it doesn't wait. The front end won't wait. It will, the messages window is showing you that both of these tabs were formatted the very first go, right? I haven't yet visited the first tab, but both the first and second have been formatted. And now they don't need to be formatted again. How do you avoid this issue? Well, if the front end didn't need to size the tab view as the largest thing, it wouldn't have to scan through all the tabs. And so the way to avoid it is to set image size to automatic. Now we see when we're viewing the first pane, the first dynamic fires. And only when we switch to the second pane does the second dynamic fire. Yeah? So I think this is very useful.
Sorry, that would be the same if you were to explicitly set the size of the tab as well.
Yes, as long as all is neither the width nor the height of the tab view, this will be fine. So automatic or a fixed number for width or height. Yes. Okay, so that's programmatic evaluation and a little bit of discussion about the dynamic primitives we have. The next principle, principle of minimal dynamics, is an attempt to express that dynamics should never try to do more than it needs to. There might be certain bits of your evaluation that don't need to be run dynamically. They can just be run once up front. And this will change for each of your applications, but I think the principle is rather accessible to everyone. So in the simplest form, here I just have a checkbox, and I have dynamic wrapped around a big block of code that I copied out of the help viewer. I think it's math or something. So we have a checkbox that, when pressed, changes the value of this symbol. This expression depends on this symbol, so whenever the value of that symbol changes, this whole expression will get rerun. The ND solve gets rerun, the density plot gets rerun, and so it takes a healthy second every time I press this checkbox for this to update. Well, you know where this is going. The ND solve certainly doesn't need to be rerun every time I change this checkbox. So as a first approximation of getting this faster, why not just wrap the dynamic around the density plot? The solution to the differential equation can just happen once. And that gives us a benefit. It's still not fast, but it's faster. And for visualization functions, we have an additional level. We can push the dynamic all the way down around the option setting, so that the only thing changing is the value of this option in the front end. The solution doesn't change. The density plot doesn't need to be rerun. And we evaluate this, and we have now a checkbox that is working as fast as it can.
But that won't provide all options, right? Like plot points isn't.
That's correct. That's correct. This works for options which are resolved by the front end. Yes. So there are places. Yeah. There are. I guess the point of this slide is pushing the dynamic down as far as you can, but no further. Yeah. In addition to just have single dynamics at the correct level, you can have multiple dynamics nested together. And here I have an academic example that attempts to show this. When you do this nesting, when you update a dynamic, that entire dynamic content gets replaced. If you have an outer dynamic and an inner dynamic, you update the outer dynamic, both dynamics get replaced. You update the inner dynamic, that can update separately all by itself without updating the outer one. So here we're also going to use this messages window to take a look at what's happening. So we have, X is in the outer, X is in the outside, and Y is somewhere inside this frame. We change the value of X, and we see X and Y changing, right? We see inner and outer echoes being produced. Whereas if we change just the variable that drives the inner dynamic, X need not change. This is just driving changes to Y. There's only inner updates happening here. Yeah. So nesting dynamics, again, a very useful idiom. Okay, and sometimes the answer to minimal dynamics is, well, can you have zero? And there are some unique features in the desktop front end that let you get by with not having dynamics and still building interfaces that look like maybe you did use dynamic. These are bonus sections, so I can't open them, but I'd encourage you to take a look. Okay, so that's minimum dynamics. Then I'm going to talk a little bit about encapsulation. And the principle of maximum encapsulation states that you should have, when you deliver your interface to someone, it should have everything that it needs and nothing extra. It shouldn't infect the user system with stuff that it doesn't need. We've already talked about two different ways that you might do this. You might deliver finished notebooks the way that the mathematical layout does. You might supply code that creates interfaces on the fly, the way that Manipulate and friends do. Common to both these approaches is use of a construct dynamic module. This is a very useful construct that we developed when first building Manipulate some years back. And it's useful for the following reasons. Why would you want to use a custom scoping construct in the front end rather than just using block or module? Well, block is fine, but it doesn't really isolate things fully. You know, it still is changing global state. Module scopes things during the kernel evaluation by virtue of these temporary variables, yeah, based on $module number, which is fine, but interfaces don't exist in the kernel's evaluation queue. They exist sort of on your, they exist in your notebooks. You make a copy of an interface. Well, I'll use my first example here. So you make a copy of an interface. Should these two have the same X? Right? I mean, this is a fundamental question. If we have manipulative X, this uses dynamic module to do its scoping. This is not the global X. The global X is not changing when I interact with this manipulate. But what if I were to make a copy of the output? Well, if this were just some output generated from some kernel evaluation of module, this would have the same temporary variables. It would be the same X. That's not good enough for manipulate. If you make a copy of this, you don't want outputs to sort of be dependent on other outputs. So we have dynamic module being able to scope things in a region on the screen rather than in a region of kernel evaluation. One way this is sometimes described is module scopes in time, kernel evaluation time, and dynamic module scopes in space, and these rectangles on the screen. Yep. So scoping is a very useful way to reason to use dynamic module. Another is that it automatically saves state for you. And if you've used manipulate, you know this. I'm not going to show an example. You have a manipulate, you slide the sliders around, save the notebook, close down, go to sleep, travel to Urbana, open up your notebook. All the sliders have the same state where you left them. This is not something that manipulate built. This was built as part of dynamic module. So it gives you this for free just by using dynamic module. Dynamic module also gives you a place to store initialization code. So in a pre-dynamic world, we had initialization cells. You open up a notebook, you try to evaluate something, you get this blob that says, I think there's some initialization here. Do you want me to run it for you? And we still support that model. But in the modern world for dynamic interfaces, that didn't really work for us because we wanted the ability to open up a notebook and have dynamics automatically start moving around. So we have dynamic module as a construct that when it is first displayed, every time an instance of this dynamic module is first displayed, its initialization option is run. And this is useful. I mean, you can imagine how this is useful for deployment. You put your utility symbols, definitions in the initialization, and there you go. It can be somewhat awkward to populate this manually, although sometimes it's useful. Other times it's useful to populate it automatically. So save definitions used to be just an option to manipulate. Now it's also an option to dynamic module. If you set save definitions true for a dynamic module, it will automatically slurp in the full definition of every symbol that appears in the manipulate. So among other things, it will get the kernel notion of full definition of the function that is referred to in this dynamic module. And it will embed that in the initialization option of the generated dynamic module. So if we were to look at the input form of this, we would see it's a dynamic module. And this dynamic module doesn't have save definitions anymore. It has a literal initialization, which was created as a side effect of save definitions true. Yes?
If you define the initialization in that dynamic module, and then you also had save definitions, wouldn't then
Yes. The question is if you use both save definitions true and a literal initialization, do they play well together? And the answer is yes. I forget which one goes first and which one goes second, but yes, they're thrown in together. Yes.
What about the X that gets initialized first argument of the dynamic module option?
I'm sorry, the X?
The X gets initialized twice, so what counts?
Yes. Marcus is pointing out that save definitions is often not what you want, because not only did it slurp in the value of my func, it slurped in a global value from x because, well, you know what? Look, there's an x there. And that's because, well, every symbol in the dynamic module is affected by save definitions. And if we look at the full definition of x, sure enough, it has a value. So this is something you should be aware of when using save definitions. It is not for everyone. And if you have global state that you're worried about getting saved, you may want to use literal initialization settings rather than save definitions. Right. Okay. I think we're right on time. So what are some other useful techniques when dealing with dynamic module? Well, just like when dealing with module, you want to be careful about how you pass local variables to other utilities. So I'm going to show sort of a common misapplication of dynamic module and how to fix it. So clearly, we want some way to break up, a code base so that you don't have an entire interface designed and deployed inside or written in Wolfram language code in a single dynamic module. Manipulate was not written as a single dynamic module in some Wolfram language code file that was millions of lines long. It's modular. And likewise, if you wanted to modularize this interface, how might you do it? Well, we have a control block. We have a display block. Maybe we can separate those out. We say, okay, I want the controls to be this, the display to be this, and then we're going to assemble those things into a column of controls and display. Looks great, right? But it's not going to work. And it's not going to work because of the details of how these variables were passed through to the utilities. It's a good architecture. I encourage you to use modular implementations, but you need to be careful about how you pass things around. So what happened here was, well, dynamic module initialized A to the value 1, and then controls of A, well, that's controls of 1. So we get controls of 1, that's slider of dynamic of 1. Well, that's not going to work. We want slider of dynamic of A. How do you handle this? Well, in the old world, you use holding attributes on your functions. You use hold first, hold all, something. I think in so you're only getting passing the value of the symbol, not the symbol itself, not the symbol by reference. And yes, you can add holding attributes. The way that I prefer to do it is to use the same model used by our control language, by passing dynamic of variable through as the argument to your utilities. So here I have controls of dynamic of variable. Dynamic is a hold first construct in the kernel, right? It's not going to evaluate its expression, its argument. So controls of dynamic of A is not going to pass the value of A. It's going to pass A by reference. And so this is a refactoring that will work. We have controls of dynamic of A, display of dynamic of A, and now the utilities get the appropriate local variable from the dynamic module, and all is good. And if you really like using hold first and hold all, you can use those, but I prefer this model. Okay, so first half of my talk was the first 3 principles. Second half is, I'm hoping, going to be filled with the last principle, the principle of evaluation blocking. This is the idea that there are 2 kinds of dynamic updates. There are updates that happen quickly. There are updates that happen slowly. And knowing when to use each can often be the difference between writing an application that's responsive and usable and an application that shows you $aborted and spinning beach balls and all kinds of other nasty stuff. And rather than digging straight into the terminology of how we express these notions in dynamic, I'm going to talk to you about grocery stores. So say you have a grocery store that has 2 checkout lanes. There's an express lane for the people that have 6 items or less, and then there's the guys who have their full carts and they can go through some main checkout lane. Further suppose that there is a single clerk working at this store. And that single clerk is staffing both of these lanes, right? And whenever somebody gets into the express lane, the clerk goes over and takes care of them right away, and then gets back to whatever they were doing in the main lane. Somebody takes too long in the express lane, they get kicked out, right? So this is essentially what's happening with our dynamic system. We have a single kernel, a single, computational engine. I'm going to shrink this just for a second. And it's servicing two different kinds of evaluations. It's servicing main loop evaluations that can take as long as you want. These are the evaluations that have been around since the beginning. You start something on a Monday, it finishes a week from Thursday. It can run and run and run. These are some of the terms that I might use to refer to them. Queued evaluations. They're asynchronous in our dynamic nomenclature. In some controls, they're called method queued, and others they're called synchronous updating false, synchronous initialization false. And there are some other ways to access main loop queued evaluations. In the express lane, the fast stuff, you'll hear me talk about preemptive evaluations on the preemptive link. You'll hear me talk about synchronous updating true or synchronous controls, and so on. So we have very much this situation in our system. And stay out of the express lane if you're going slow. And I'll come back to that. Let me go back up for Jason. Okay. So letting slow things be slow. There's no shame in a computation taking more than a few seconds, but you do need to accommodate it in your interfaces. Any interface that asks the user for something in a blocking way, so if you use system dialog input and try to call that from a button, this first input is going to fail because some users are going to interact quickly with this interface, and they'll get in under the, 6-second deadline for preemptive evaluations. It's not just that they should be fast, it's enforced that they are fast, and if they take longer than a few seconds, the front end will actively kill them. So if you expect your users to be that fast in a dialogue, you're in for a world of hurt. This is the right way to do that for buttons. You tell the button, you know what, this might take a while, so use the queued link. Use a queued evaluation here. When interacting with the network, I'm not going to bother evaluating this because I understand that the network is rather flaky here in this room. Whenever interacting with any network, known or unknown, it might take longer than you think. There might be some network hiccups. There might be something going on with some DNS server somewhere. Use asynchronous updating. Use queued evaluation in this case. So here we have a call to the pathable API. Maybe I'll try evaluating this. So this is going to go off and, that wasn't so bad. So notice that gray rectangle, that was the front end saying, I have stuff that's coming back for this, hold a place for me. So use synchronous updating false whenever you have network transactions. Whenever you have a complicated graphic or an extensive report that might take more than a few seconds, use the slow lane. Anything that might take more than a couple seconds, use the slow lane. Otherwise, I'll try evaluating. I even made those unevaluatable. Wasn't I clever? So synchronous in the dynamic module world, that's synchronous updating false for dynamic. And for a long-running dynamic module initialization, it's synchronous initialization false. Right. Okay. So building on that, we have these two lanes. We have evaluations happening on both of them. Are there interesting things that can be done by employing both links simultaneously? Well, since I'm up here in front of you and I asked the question, the answer is probably yes. So one nice way that we've built on top of having these two links is being able to show you what's going on with an evaluation while it's happening. The kernel has always had this notion of dialogues or subsessions, and the preemptive evaluation sort of formalized that. And here we have a stack of technology that while it's running, so I've used Shift-Enter to kick this off. That's a queued evaluation, a long-running do loop. in the first argument to this monitor. Oops, I meant to reevaluate the first one. So that queued evaluation is happening. During that queued evaluation, there are dynamic updates happening synchronously. So the first thing this monitor does is it prints out dynamic of I. And then that synchronous dynamic can update during this queued evaluation. So we have a long-running evaluation triggering updates and shorter-running evaluations. And the monitor that gets printed can have any form. I mean, this is Mathematica. You could be arbitrarily clever here. We have dedicated progress indication kinds of things. But I mean, you can build your own. You can do all kinds of stuff, right? And there are a couple of other primitives that I've listed here that you might be interested in if you're interested in this kind of stuff. And as I said, what's really happening here is you have a queued evaluation that happens to be setting a variable, and that changes to that variable are triggering these other dynamics to update. And here I've kind of teased that apart a bit. I have a queued evaluation, this time being started by a button, not by a shift return. And I have a synchronous dynamic that's watching the value of a particular variable. And by clicking this button, during the evaluation of that button function, I guess I should maybe highlight what that button function is. During the evaluation of this do loop, the global value of C is changing, and this other dynamic is watching the global value of C, and every time it changes, it kind of picks a new value. It's not showing all of them, notice. It's showing them at about 20 a second or so. But so this is the kind of approach. This is a very useful approach when you want to provide some sort of feedback in your interfaces for long-running evaluations. I remember hearing not long after I started working at Wolfram that Apple tweaked the speed of the spinning beach ball, because even though the computer was stuck not doing anything, the speed at which the beach ball spun gave users more of a good feeling. If the beach ball was spinning faster, that meant, everything's okay. So as interface programmers, I'd encourage you all to make sure that your users know what's going on in your interfaces. And I'm not going to run this second example because it doesn't work. It's there as an example of what not to do. And these are built out a little bit more. You can look at these at your leisure. It's the same kind of thing, a queued button driving a long-running evaluation, and a synchronous dynamic showing progress. In this case, it shows both progress and what happens when the evaluation completes. So we have a spinner, and then it's replaced by the result of the evaluation. I'm going to come back to this example in a little bit and tell you why it's not quite good enough for production code. It's pretty good, but it's not quite good enough in the wild. Another thing I'll mention, as long as we're talking about method options, is, I don't know if we made a big to-do about this, but we did add method support to Event Handler in version 10.2. So I think method queued and method preemptive were only supported by button and action menu prior to that. And now we have support for that in Event Handler, which can be very useful. Here's an example. So button in graphics uses Event Handler. So queued buttons in graphics, wrapped directly around graphics primitives, used to not work. But now it does, because we have button, which based on Event Handler, now supports method queued. So here we have a graphic that when you click it, goes off and does nothing for a second and then changes the color of the disk. Yep. It's kind of fun, actually. Okay. So what else is there to say? Well, there are some other interesting uses of having these two links. One you may have noticed all on your own. So if you had a complicated visualization function, plot 3D, parametric plot 3D, something like this, you start dragging around controls, you notice the mesh lines go away, and you get this sort of jagged display. It's fast, but it doesn't really look all that great. And then when you release the mouse, things snap back into focus. The mesh lines come back, you get this beautiful rendering. How does this work? How can I use this in my own interfaces? Well, there's two pieces to this. There's a new wrapper called control active, and there's a setting for synchronous updating that I haven't talked about yet. So control active takes two arguments. It takes basically a fast rendering and a beautiful rendering. The assumption that the fast rendering is going to evaluate quickly, the beautiful rendering might take a little bit longer. But it's just a wrapper that contains sort of two things and automatically switches to the fast rendering while you're interacting with controls and to the slow rendering when you let them go. Synchronous updating automatic is the front end's way of saying, I know better than you do when it comes to deciding which links to use. And when the front end decides which links to use, it can switch back and forth between them for the same dynamic. So it can say, for some updates, I'm going to use the preemptive fast lane, and for others, I'm going to use the queued slow lane. You put that together with control active, you have a fast preview that gets through on the preemptive link. Notice, among other things, that the cell bracket is not highlighting here. All of these evaluations are preemptive. And as soon as I release this, cell bracket highlights, control active switches to the other state, and that beautiful rendering now goes to the queued link and can take as long as it wants to come back. Of course, this is exactly what you want for responsive interfaces. You don't want every drag of this slider to have to take 5 seconds to produce a new beautiful graphic. You could certainly produce a better fast rendering by direct use of control active. And here I have sort of an example of direct use of control active. Again, it's a dry academic example, but hopefully it gives you a flavor for what's happening. We have a slider, and we have a control active and a dynamic. The fast rendering is just the value of the variable. The slow rendering, the artificially slow rendering, is the value of the variable in a panel. With synchronous updating automatic, the magic happens. So we drag the slider, we see just the value. We let go of the slider, takes a second, comes back with the beautiful rendering. Anything at all can go in the first or second arguments to control active. So here's an example of a solution to a Stack Overflow question from a couple years ago, I think, where control active, its fast rendering is sort of a simple graphic. Its richer expression is not just another graphic, it's a dynamic module construct with an asynchronous initialization. So this control active payload fills in a little at a time. So we drag this around. Fast rendering is just a purple circle. Slow rendering goes off and runs some iterative thing where the graphic is being updated over time. And now we're done. Okay. So some of you may have found the option that controls how fast, what the throttle is that the front end uses for preemptive evaluations, what the timeout setting is. I encourage you not to change that value. Instead, as interface programmers, design for things that are slow to use the queued evaluation modes and things that are fast only to use the preemptive modes. Yeah. Okay. So we've seen how queued evaluations can affect synchronous updates, or can trigger synchronous updates. I'd like to show you sort of the opposite. So we have button, event handler, action menu are controls that can directly kick off queued evaluations. What if I want a queued evaluation kicked off by a checkbox or a radio button? How do I do that? Well, turns out it's not that hard. And here's one example of how you might choose to do that. I'm using a construct dynamic wrapper. It's a lot like dynamic, except it lets you say what you want to display and separately say what you want to track dynamically. It doesn't display the thing you're tracking dynamically. So it's going to display as a checkbox attached to a dynamic variable. And its payload, the thing that it's going to update, is, well, if this variable is in the true state, then it's going to run some other code. It's going to do that asynchronously. So this checkbox, a synchronous control, is going to kick off an asynchronous computation. And the net effect of that is, we have a checkbox. Note the cell bracket lit up, and this goes off and works for a while and comes back. So we have switching to the false state, nothing happens. Switching to the true state, goes off and percolates for a while and then comes back. So there's a lot of flexibility with having these evaluations happening on one link, triggering evaluations on other links. But it really does require that you put a little bit of thought into how these things are architected. People who are seriously interested in these kinds of things, I would encourage you to take a look at Todd's very fine essay on Stack Exchange about preemptive evaluation in general and preempt protect in particular. I don't see Todd in this room, but he's at the conference. Very useful information on this page, well beyond the scope of this talk, but I think it would be useful to people who want to take their knowledge up a step. So that's preempt protection. There's also some abort protection that one can leverage. And remember, a few slides back, I told you that there was a button that didn't quite work as well as it could have. Well, that's because, users are finicky, and they can change their mind. They kick off some long-running evaluation, and maybe they'll sit there and let it complete, or maybe they'll try to interrupt it or abort it. Here we have an interface. The user has successfully aborted. This evaluation is not doing anything anymore, other than continuing to show you evidence that maybe it's doing something. But it's not doing anything. The evaluation is done. The queued evaluation, the cell bracket is not lit up anymore. There's nothing happening here other than a spinner spinning on screen. How can this be refactored? Well, the kernel has a couple of constructs for absorbing aborts in certain ways. There's abort protect, and check abort. There's ways to determine if an abort has happened in a certain body of code, and if so, to run some cleanup. And there's a way to say, if an abort happens in this body of code, ignore it until this body of code is complete. So by adding those kinds of awareness to this button function, we can say, we can detect aborts in our main thread of evaluation. And if an abort is detected, then go do some cleanup. Right? So here we have, if things evaluate all the way through, there's nothing to see. If you abort, then this goes into a cleaning state and then tells the user, yeah, okay, you win. Right. So, quite a little body of code, but if you have users that like aborting things, this is the kind of thing that you'll need to do. And I promised myself this would be a bonus slide, but I will at least give you a flavor for it. So imagine you have a monitor, and you know what percentage of it's done. You know how far along it is in your do loop. But you also know that the evaluation it's progressing through is very regular in the speed with which it needs to handle every step. In that case, the monitor could, in principle, give you an estimate for when the evaluation would be complete. Should I show this example or not? Yeah, okay, I'll show it. I won't show the implementation. I won't show the implementation. But if you have a very regular evaluation, this is not going to sort of automatically give you a countdown timer for integrate. If you happen to know that your things are very, very regularly, there's a cadence to the evaluation that doesn't change much over time, then you might add this kind of monitor. And the code is left in this closed bonus section. I encourage you to get the notebook. And that's really all I wanted to talk about. So, and we have the ideal 10 minutes for questions. Yes?
Is there a way, so you said some options are front-end handleable, some aren't. Is there a way to figure out which are which other than just playing with it?
Playing with it is a great way. It requires a little bit of knowledge about the box structure. I don't know if you went to Jason's talk immediately before this one, but you would need to know things like the frame option for density plot maps to the frame option for graphics box, whereas the plot points option maps to a different branch of the plot kernel evaluation. You can get lists of box options. And, I mean, so you can look in the option inspector to get a list of graphics box options, for instance, to get an awareness of which options are likely to be immediately passed through like this. Yeah. It's going to be a long 10 minutes if I'm just standing here quietly staring at you. Yes.
So getting back to this dynamic module case.
Yes.
You initialize the variable x in the first argument, but the function in the last option argument.
Yes.
Why? What's the difference?
So the question is, let me see if I can find the example. The question is, when we looked at the details of this dynamic module, which was created automatically by save definitions, it says 2 definitions for x, right? Takes a keen eye. 2 definitions for x. There's one there, there's one there. Why? Well, really this is an artifact of having used save definitions to build this initialization section.
That's not my question. Even if you can build this up there, on the top of the slide, you write x equal 1, that's initializing x. But the function itself, you initialize in that case by an option initialize. You could also put the function definition up there where the x equal 1 is.
So the question is, how is the first argument to a dynamic module different from the initialization option to dynamic module? Is that the question? Okay, so dynamic module attempted syntactically to mirror the syntax of module. And when you define things in a module, you don't put down values in the first argument to a module. You put own values there, but you don't put, f of x colon equals blah. You put f, right? In your module declaration, and then you define f in the body of your module. And that's the paradigm that we followed for dynamic module. So the first argument is where own values are stored, and then everything else is actually stored in a part of the expression that you don't see until you look at. So own values are stored in the first argument. Everything else is stored somewhere else in the dynamic module. Does that?
Well, you don't have to, do you? You can still put it up front.
Put what?
The definition of my fun.
Into the first argument? But syntactically, that's a no-go. So you're saying I could do this. You're saying we could have had support of that. And module could have supported that too. But module didn't, and we weren't going to break the mold. So you're suggesting this. And this is invalid in the module world, and it's invalid in the dynamic module world. Yes, but I mean, maybe in an alternate universe, we could have supported something like this. Yep. Yes.
I just wanted to shout out something that I found quite useful, because I'm not quite remember what exactly it's called, but it's like a way of attaching a dynamic to a notebook or a cell. What's that called again?
Okay, the question is, I don't really remember this thing, but isn't it cool? Maybe that's over. So there's a notebook dynamic expression, cell dynamic expression. There's even a front end dynamic expression. And these are, let's see, we saw a version of that in this talk. We saw the outlier, the one that was named as an outlier. Let me see if I can find it. It was the asynchronous checkbox. So dynamic wrapper is sort of the box version of what you described. It's the ability to attach an arbitrary expression that updates dynamically for whenever the box is on screen. But you can have the same thing attached to whenever a cell is on screen, or whenever a notebook is on screen, or whenever the front end is present. And yes, those are front end dynamic expression, notebook dynamic expression, cell. So what have you used those for? You said they were useful?
I think I used one. I had a system where if you typed into a notebook, it would annotate the text cell that you created with your username. So people shared a notebook, you kind of had a record of who typed what. I think I used that because I needed to delay attaching that label until I knew who it was. That's the dynamic type of thing.
There are a couple of other hooks, again, getting back to the non-dynamic cases. Notebook dynamic expression, I think, is useful, but there's also notebook, there's cell prologue and cell epilogue, which are things that are evaluated before and after your cells are evaluated. And setting those at the notebook scope can often be a useful thing. There's also event handlers that you can set for a whole notebook to change what Shift Enter does on a notebook, or change what typing the letter X does in a notebook, or in a cell, or throughout the front end.
So getting back to this, if we go to slide 21, and you've got this example here of the slider.
Oh, where are the numbers? Is that around 21? Oh, good guess.
So here we have the slider, and we've got the synchronous updating goes to automatic.
Yep.
If we change that to true, and we take a look at its behavior, and we change it to false, and look at its behavior, it's all fairly similar.
It's similar, but it's not the same. And in fact, yes. So watch the cell bracket. Synchronous updating is true. Watch the cell bracket as I release. So both updates are happening on the preemptive link. So if your fast rendering is fast enough to happen on the preemptive link, that's fine. Now,
You put a strategic pause in there so you can buffer.
yes. Are you asking me to do that?
Yes.
Okay. So let's change that 1 to a 7. And I don't even have to actually, well, let's see, what did I do wrong here? Ah, it's busting. So there you go. And so if I started to drag this around, it's not even going to switch over, because Jason broke my example. Okay. Right, but synchronous updating true, so both are happening on the preemptive side. Synchronous updating false, both are happening on the, oh, I've really busted things. Okay. Where is it? What am I doing? There we go. So now notice that even when I'm dragging the slider around, the cell bracket's blinking away, because even these are happening as queued evaluations. 5, 6, 7. Okay. Okay.